Something impossible is happening right now above our heads, and scientists are scrambling to understand it before it's too late. A cosmic visitor just exploded in brightness while hurtling toward us, and at the exact same moment, our star fired its most violent burst in months directly at it. What happens next could rewrite everything we thought we knew about space. September 12, 2025. The discovery moment. A frozen wanderer from the outer reaches of our solar system, designated C/2025 and nicknamed Swan, swings dangerously close to our star. The distance measures barely half the space between Earth and Mars. Initial readings seem ordinary. Brightness levels hover around 7.4 on the magnitude scale. The glowing tail stretches a modest 2 degrees across the darkness. Nothing to write home about, right? Wrong. Comets hide secrets beneath their icy shells, and Swan is about to reveal something extraordinary. 2 weeks pass. September 26th arrives. Sky watchers in Japan and Australia notice something strange through their telescopes. The numbers start jumping. Swan's brightness suddenly surges upward by nearly a full magnitude in just hours. What was invisible to the naked eye now becomes visible even without equipment under dark skies. Online astronomy communities explode with activity. Fresh measurements confirm the impossible. 5.7 magnitude, then 5.8. The glow holds steady through September 28th. But what caused this dramatic transformation? Deep within the comet's frozen nucleus, volatile pockets of ancient ice and gas have been hiding for millions of years. As Swan passed close to the sun's scorching heat, these pockets reached their breaking point. The pressure built up until the surface cracked open. Jets of gas and dust erupted violently into space, swelling the glowing cloud around the nucleus and feeding the magnificent tail. The transformation happened in real time. Every new observation revealed more about the chaos unfolding beneath the surface. Thermal stress, explosive venting, possible structural collapse. Some observers spotted jet-like features near the core, evidence that new cracks were tearing through the ancient ice. The comet had entered unknown territory, and nobody could predict what would happen next. Now picture this tail stretching across your night sky, 2.5 degrees wide. That equals 5 full moons placed side by side. This isn't some tiny fuzzy dot lost among distant stars. This is a massive structure you can trace with ordinary binoculars. Even from light-polluted suburbs, the streak demands your attention. The sheer scale means the comet's inner workings are now on full display. Knots of dust particles, shifting rays of light, the faint electric blue glow of ionized gas, all sculpted by radiation pouring from the sun. The tail's architecture tells a story written in real time across the cosmos. Heavier dust particles, slower to move, linger close to the comet's path, forming a broad fan lit by sunlight. Meanwhile, the ion tail, lighter and more volatile, can snap like a whip, ripple like water, or even break completely away under the right conditions. With Swan's tail now covering more sky than any city skyline, even amateur telescopes can pick out incredible details. Streamers, kinks, sudden bends. For observers tracking the show night after night, the changes aren't subtle at all. A single evening can reveal a completely new twist, a fading plume, or a sudden brightening as fresh material streams from the nucleus. The global community of comet watchers responds immediately. Amateur astronomers across every continent stack their camera exposures, compare detailed notes, and share time-lapse sequences revealing tail movements hour by hour. Discussion forums light up with reports of subtle color shifts. Icy blue indicates ions. Golden yellow signals dust. Each color hints at the complex chemistry happening in real time. Swan's position low in southern skies during September and October favors observers from Australia, South Africa, and Argentina. But even northern viewers get their chance as the comet climbs higher and the moon fades away. For anyone with even modest binoculars, the coming weeks offer a front row seat to solar system physics happening live before your eyes. Yet the tail's impressive reach means more than just spectacle. It sets the stage for what happens when our star sends its own shock wave into that same region of space. The real question becomes not how long the tail will grow, but how it will react when the solar bombardment arrives. September 28th, 0843 Universal Time. The sun strikes back. Our star erupts with an M6.4 class flare, the strongest in months. For most of September, solar activity had been unremarkable. Energy output readings from monitoring satellites showed flat trends, suggesting a quiet period in the current solar cycle. Then, without any warning, the monitors spiked dramatically. The flare's energy output, measured in millions of kilowatts, lights up real-time monitoring charts at space weather centers worldwide. Solar scientists scramble to assess the situation, cross-checking data from multiple satellite observatories. This is not just another routine solar hiccup. M-class flares sit in the middle tier of the solar eruption scale, but an M6.4 is powerful enough to catch the attention of satellite operators and space weather forecasters everywhere. The flare originates from active Region 4232, a complex sunspot cluster with twisted magnetic fields. More importantly, it sits in the same sector of the Sun that Swan is now approaching. Within 30 minutes, specialized cameras confirm the launch of a coronal mass ejection, a massive cloud of superheated plasma. The initial velocity estimates range between 800 and 1,000 kilometers per second, placing it among the fastest eruptions recorded all year. Inside operations rooms, alerts ripple outward. Satellite teams check their protocols for radiation spikes. But here's the twist. This plasma wave is not heading toward Earth. Instead, the focus shifts to what lies directly in its path. The timing, occurring just 2 days after Swan's mysterious outburst, draws immediate attention. Duty officers flag the event for comet researchers, who begin modeling the possible intersection between the racing plasma cloud and Swan's expanding ion tail. The numbers paint a clear picture. An M6.4 flare at 0843 Universal Time. A plasma wave racing outward at nearly 1,000 kilometers per second. And a comet with a tail spanning more than 2 degrees sitting directly in the line of fire. The Sun, quiet for weeks, has sent a powerful pull straight into the same sector where Swan is putting on its own dramatic show. This intersection of events is extraordinarily rare, and every scientific instrument from orbital detectors to ground-based telescopes now has a compelling reason to watch closely. Racing against time, the tracking challenge. Inside space weather prediction centers, the race began the instant the flare peaked. Analysts pulled up real-time feeds from multiple satellite coronagraphs, scanning through image frames for the expanding arc of plasma. The mass ejection launched just after 0845 Universal Time, fanning outward with an initial velocity near 900 kilometers per second, fast enough to cross the average Earth-Sun distance in less than 48 hours. Its angular width measured approximately 90 degrees, placing it among the broader ejections recorded all year. But the crucial detail was its trajectory. This time the blast missed Earth by a significant margin. Instead, computer model overlays revealed the main lobe sweeping directly into the sector of space now occupied by Swan. For forecasting teams, the challenge was pure geometry. Solar eruptions don't travel in perfect straight lines. They expand, twist, and sometimes fragment as they plow through the surrounding solar wind. To chart the plasma cloud's path, scientists stitched together coronagraph images, plotting the leading edge against known positions of planets, spacecraft, and for the first time in years, a comet with a tail longer than 2 degrees. Swan's coordinates, positioned just inside Earth's orbit and slightly south of the orbital plane, place it near the predicted corridor. But three-dimensional uncertainty remains significant. Without a direct Earth impact, detailed plasma data would be limited, leaving ground-based and orbital imaging as the best tools for tracking the encounter. Every major forecast center flagged the event for comet researchers worldwide. The burning question hung in the air. Would the plasma wave's broad front actually intersect Swan's tail, or would it sweep harmlessly past? Best estimates place the arrival in the comet's vicinity between 48 and 72 hours after launch, depending on the true trajectory and sustained velocity. Density projections suggested a moderate event, strong enough to disturb the ion tail significantly, but unlikely to trigger any effects on Earth. For our planet, the risk was minimal. For Swan, the incoming solar plasma set the stage for a possible spectacular display. Tail kinks, complete disconnections, rapid changes unfolding on timescales of mere hours, visible to anyone watching the right patch of sky. The scientific tools were ready. The data streams wide open. Now all eyes shifted toward the comet corridor, waiting for the collision. The invisible force, magnetic fields, and cosmic scissors. Magnetic fields determine the fate of every comet tail caught in the solar wind's path. When a coronal mass ejection like the one launched on September 28 sweeps across space, it drags along a tangled web of magnetic field lines, each one carrying its own unique orientation. The ion tail of a comet builds from charged particles stripped away from the nucleus and pushed outward by the constant flow from the sun. These ions don't simply drift randomly. They cling to magnetic field lines, forming an invisible tether stretching millions of kilometers behind the comet. But the real cosmic drama begins when those field lines meet the boundary between the comet's tail and the incoming solar wind. If the magnetic field embedded in the plasma wave points southward, opposite to the typical direction near the comet, conditions become perfect for what physicists call magnetic reconnection. This is the cosmic equivalent of a circuit breaker violently snapping open. Field lines from the solar wind and the comet's tail collide with tremendous force, snap apart, and rapidly rejoin in completely new patterns. The process releases enormous energy and can cut loose entire sections of plasma. In practical terms, this means the comet's tail can break away in minutes, sending a glowing fragment drifting off into deep space while a new tail begins forming almost immediately. The orientation of the plasma wave's magnetic field, especially what scientists call the B sub Z component, determines the strength of this effect. A southward field is the trigger most likely to sever the tail cleanly. A northward field can slip by with little more than a gentle ripple. The process happens incredibly fast, sometimes visible within hours. It can leave behind dramatic kinks, sudden brightness drops, or even a detached cloud of ions moving independently through space. For theoretical physicists and computer modelers, this represents a rare opportunity to witness magnetic reconnection playing out on a scale no laboratory on Earth can possibly match. With every twist and break written across the night sky in real time, every hour now counts critically. The window for dramatic transformation is wide open, and the rules are beautifully simple. Watch the tail carefully. Trust what your eyes and instruments reveal, and keep your expectations flexible. What could happen next? The watching window, Swan's ion tail, stretching more than 2.5 degrees long, stands exposed to the full force of the solar wind. If the plasma wave's magnetic field lines intersect the comet's path at the right angle, the ion tail could kink sharply or snap away completely in as little as 90 minutes. A process that for most comets unfolds silently in deep space, but now plays out on a stage visible to backyard telescopes worldwide. Spectral signatures may shift abruptly, with hydrogen and oxygen emission lines drifting by up to 50 kilometers per second as the plasma reacts to the shock wave. The tail's shape and structure can change on timescales shorter than watching a movie. A bright filament might break free and drift away. A completely new tail could form in the wake of a disconnection event. This is science unfolding at real speed, and remarkably, the best observational data may come not from billion-dollar space telescopes, but from citizen scientists. Anyone with a camera and clear skies can contribute meaningful observations. But caution remains essential here. Not every ripple or sudden dimming proves a solar storm interaction. The geometry of the plasma wave's exact path is still an open question, and predictions about direct encounters remain hypotheses, not established facts. Experts urge careful vigilance, not premature certainty. The correct scientific response is to document thoroughly, compare observations across locations, and report findings, building a global record as the comet's story continues unfolding. For now, the only guarantee is change itself. The next anomaly could appear in a single photograph captured from someone's backyard, and the entire world is watching together, waiting to see what unfolds. October 21st, 2025. The ultimate close encounter. The orbital mechanics tell a compelling story. Swan will pass just 0.25 astronomical units from Earth, approximately 39 million kilometers, roughly 100 times the distance to our moon. For a comet, that represents the planetary equivalent of a close flyby. This isn't some random cosmic coincidence. The geometry aligns almost perfectly. Swan's orbit crosses the orbital plane at a shallow angle, riding the same invisible surface that defines our solar system's main traffic corridor. The comet's position just south of this plane places it squarely in the zone where solar wind activity and the heliospheric current sheet are most dynamic. On the exact same date, another cosmic wanderer, interstellar visitor 3I/Atlas, reaches superior conjunction, positioned directly opposite the Sun from Earth's perspective, while Swan sweeps through its closest approach point. Both objects, separated by millions of kilometers yet sharing the same broad corridor, offer scientists a rare opportunity to compare native solar system dynamics with interstellar behavior side by side. For orbital analysts, this alignment represents a statistical outlier. The probability of two such bodies, one from deep within our solar system and one from interstellar space, converging near the same plane within days, is vanishingly small. The timing adds another layer of perfection. October 21st brings a new moon phase, erasing all lunar glare and creating the darkest possible skies of the entire month. With Swan at its nearest approach, the parallax effect becomes measurable even to modest backyard telescopes. Tiny shifts in apparent position as viewed from different points on Earth's surface. Sky position calculations show Swan climbing higher each night, its magnificent tail tracing a path across southern constellations. The gap between Earth and the comet, mapped in real time, shrinks to merely 1/4 of the Sun-Earth distance. This offers the absolute best possible observation window before Swan recedes back into the depths of space. Your viewing guide: how to catch the show. For anyone hoping to witness Swan in the coming nights, timing and preparation mean everything. October 21st is the headline date to remember. Closest approach: new moon, the darkest skies of the month, all converging. But the viewing window stretches wider than a single night. Swan's trajectory runs just south of the orbital plane, climbing higher each evening through southern constellations. From Buenos Aires to Perth, the comet rises early and lingers well into pre-dawn hours, its tail sweeping westward across the horizon. In northern latitudes, the view improves steadily as October progresses. Swan peaks above the tree line after midnight and gains altitude each successive night. Star charts place Swan near the border between Grus and Piscis Austrinus constellations. Easy to locate if you trace an imaginary line from Fomalhaut, the brightest star in that region of sky. The tail's orientation favors side-by-side comparison with background stars. 2.5 degrees of length means the comet's trail can be measured against the angular gap between Fomalhaut and its nearest stellar neighbors. For binocular users, a standard 7x50 field of view covers the entire tail structure in one sweep. Small telescopes reveal intricate details, but even a basic camera mounted on a tripod can capture the streak with exposures lasting just a few seconds. The parallax effect comes into play as Swan closes the distance. With the comet positioned just 0.25 astronomical units away, its apparent position shifts ever so slightly depending on your precise location on Earth's surface. an effect measurable with just a few hours of patient observation and careful measurements. Amateur imaging teams are coordinating efforts across continents right now, logging rise and set times, sharing image overlays to track the tail's nightly transformations. The observation checklist is elegantly simple. Note the comet's position carefully. Sketch or photograph the tail structure. Watch closely for kinks, sudden brightenings, or unexpected fading. Every single observer, whether viewing from city glow or pristine rural darkness, adds another pixel to the global picture being assembled in real time. This is your moment to join the worldwide watch. The final word: what we know and what we're about to discover. This rare, cosmic timing has set up a documented encounter unlike anything in recent years. As Swan approaches its closest point to Earth on October 21st at approximately 0.25 astronomical units, scientists worldwide are monitoring for direct observable effects between the solar plasma wave and the comet's ion tail, a phenomenon scientifically known to cause rapid visible changes in comet structure. However, complete honesty demands acknowledgement. The exact outcome of this particular solar-comet interaction remains in proven territory, and no direct causal link has been definitively established between the recent solar flare and Swan's earlier brightness outburst. What stands verified beyond doubt is this: throughout October, both amateur and professional observers possess a unique window to witness cometary dynamics and solar interactions unfolding in real time. As documented through the global observation campaign now underway, Swan's journey represents a rare opportunity to track cosmic forces at work, with key scientific results still unfolding night by night above our heads. The story isn't finished yet. The most dramatic chapters may still be waiting to be written across our night sky. If you're passionate about space mysteries, cosmic encounters, and witnessing rare astronomical events as they happen in real time, this is exactly the kind of content you need to stay updated on. Subscribe now, so you never miss the next cosmic event that could change everything we thought we knew about our universe. The cosmos doesn't wait, and neither should you.